All right, let's go ahead and get started again. Today I'm going to be moving on into section or chapter 4, section 4.1, 4.2, finish up 4.1, go into 4.2, maybe even dabble a little bit in section 4.3 before we stop. I know that we're about to have our next test, and so, but I bought you a little bit of time on your homework set. So when is your homework set or sets actually due? And that is, you go down here and you got your traditional homework set is due just before class, so turn into class. That'll be Thursday, so if you haven't finished it yet, please do so. And your online homework is actually due at 11:59 p.m. that evening. And so my goal here is on Thursday, I'm going to stop and actually go over homework number 3 and 4 with you guys and talk about, strategies after you turn it in. If there's any last minute questions, of course. And then get you guys prepared for your test. And if you don't have that many questions, well, then I will just move on to chapter 5 and 6 and 7. But if you do have questions, it's a great time for us to actually go over some stuff. So what I'm telling you is bring your questions to next class. If you've got some questions on the chapter 2 and 3 material, if you got questions on that, it's a great time to bring them to class because I'm going to dedicate that, pretty much that class period, to doing that. Obviously, the next Tuesday, which is what, the 3rd or something like that, is when our test is going to be. And then after that, I'm going to finish up chapter 4, move on into chapter 5, maybe dive a little bit of chapter 6. We'll have our last test. And by the time we've done all that good stuff, it'll be ready for getting close to final exam time. So you see how I'm progressing through the book and stuff like that. But for next class, we're going to sit there and focus on the test material. So if you have questions, let us know. All right. So let's go ahead and get started on today's awesome lecture, picking up where we left off. Now, I put this up there last time, but I kind of want to go through it one more time just to make sure you guys understand it. It is the definition of a vector space. What actually is a vector space? Now, we've been playing with vector spaces ever since pretty much the beginning of this class, but we're really defining it now. So that's really a big part of what chapter 4 is going to be, is we're going to bring in a bunch of these definitions. We're going to introduce new definitions and bring in old definitions, especially from chapter 2, and actually look at it from more of a theoretical perspective, but then also do some applications on it. So, a vector space, a non-empty set V of objects called vectors, which there are 2 operations: an addition on the vectors and a scalar multiplication. So you don't actually multiply the vectors; you multiply a constant times the vector, which must hold to the axioms below. These rules must hold, aka be true, for all vectors u, v, and w in set V, and for all scalars c and d. So when we talked about, again, these last times, there are 10 properties of what it is to be in a vector space. And that is closure. If I got 2 vectors, arbitrarily 2 vectors, the sum of those 2 vectors must be inside my vector space, okay? We have commutativity. It doesn't matter what order you add these vectors. U plus v is going to be the same thing as v plus u. If you've got 3 vectors you're adding, it doesn't matter what order you add them in. You can add the first 2 guys, notice the parentheses of u plus v plus w would be the same thing as taking u and then adding it to the v plus w. Now, order of operations, you do what's inside the parentheses first. Honestly, it doesn't matter. Moving around parentheses is called the associativity property under addition. There's going to always exist in a vector space a 0 vector. 0, 0, 0, whatever the look of that vector space is, there's got to be a 0 vector in there. Okay? And when you take that 0 vector and add it to any other vector, it doesn't matter what side you add it on, you'll get the other vector back again. There's going to be an additive inverse vector. That is, quote unquote, the negative vector. Any kind of vector that in a vector space, the negative vector has to be there too, such that when I take the vector, add it to the negative vector, it should completely cancel out, and you're left with the, quote, 0 vector on this thing, okay? And for scalars, starting at number 6 through 10, you've got scalars for any scalar c and a vector u. C times u has got to be in your vector space. So scalar multiplication must hold a closure under scalar multiplication, if you will. And it doesn't matter if you take two scalars, add them together, and then multiply by the vector, or multiply the first scalar times a vector plus the second scalar times that same vector. It's going to be equal to the same thing. So in other words, you can distribute vectors, you can distribute scalars. You got a distributive law for vectors, a distributive law for scalars, and they're going to be the same thing. And when it comes to your scalars, it doesn't matter what order you multiply them and then multiply times your vector. It's going to be the same thing. And the last thing is, in terms of scalars, there's got to be this number 1 out there. When I multiply the vector times 1, I should get the vector back again. That's called the identity scalar, if you will. Okay, and again, just some results of this. Okay, again, I discussed last time with you guys, but just going to put it in there again, and that is this. The 0 vector in V is going to be unique. If I'm dealing with, for example, a vector, R is something like an R3, the 0 vector is going to be 0, 0, 0. In R2, it is 0, 0. In complex numbers, it's 0 plus 0i. In polynomials, it's 0 plus 0t plus 0t squared plus 0t cubed. Now, however the vector space looks, there's got to be some type of 0 component to it. The 1 as a scalar is going to be unique. For any vector V, any vector U inside of your vector space V, the negative U is going to be unique in V. And if you multiply a scalar 0 times a vector V, you get the 0 vector. A scalar times a 0 vector gives you a 0 vector. And negative U vector, a negative U vector, the additive inverse, it will be the same thing as looking at it as negative 1 times U. And again, the last thing I talked about before I let you guys go last time were some examples of vector spaces. Now, some of them you should be familiar with, the famous Rn. R is real numbers to the n column. That tells you the number of components. So you've got, 3 components here, R3, A, B, C in order, R4, R5. These will be, this is a vector space. The set of all arrows in 3D space where 2 arrows are considered to be equal if they have the same length and point in the same direction. So I can get a vector space that is visual. I didn't actually write out numbers or components on this thing. I'm drawing these guys. But if you look at it, you can actually get that aspect out of it. But as long as you can still those 10 axioms hold, you can declare it to be a vector space. Here's one that throws people off is the old Pn. This is the set of polynomials of degree n, Pn. And so P of t would be a0 plus a1t plus a2t squared plus a3t cubed plus dot, 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 plus ant to the nth. You stop at n because this is p sub n. This is a polynomial, and you notice that the degree of this term is going to be, as long as an is not 0, will be n. And the degree of a constant would be 0, excuse me, degree of a polynomial is equal to 0 if and only if the P of t is equal to a constant, not 0. We got to sit there and talk about the 0 polynomial. We got to make him special. So we talk about the degree of the constant. 0 is actually negative infinity. It makes the math work out right when you're looking at it from a degree perspective. So that's a special case of the constant. Any other constant, 1, 2, 3, 45, 7/3, square root of 2, whatever constant you're playing with, the degree of that is always 0. Another one that throws people off in terms of vector spaces is the set of real valued functions. What's a function plus a function? Another function. That's called closure. You can multiply a function times a constant, a scalar, and you still got a function. So this is the idea of real valued functions. Anything that holds those 10 properties can be considered a vector space. Real value problems are going to be that case. Another one is like the set of continuous functions. There's a classic one that's a vector space. What's a continuous function plus a continuous function? A continuous function. When you multiply a constant times a continuous function, you get a continuous function. Look at 0. What does 0 look like? It's a horizontal line because it's called the x-axis. It's continuous, and it's 0. So, the 0 vector is in there, the 0 function. So that's going to create a set of a vector space. So again, lots of them to choose from and stuff. But what we're interested in today, again, I was just reviewing for what we did last time, is this. So picking it up from where we left off, I want to look at, quote, subspaces. Because let me tell you the real deal. We're trying to get you guys into this math proof thing. So we are looking at proving things from an elementary perspective. But here's the big deal. If I'm going to prove I have a vector space, I have to show you guys 10 things. That's why 10 things. Got to make sure every property holds for a vector space. But I can do it, but it takes several sheets of paper to be able to do that. Something that is equally important is something called a vector subspace. A subspace is a space in its own right, but if you've got this overriding vector space where it comes from, you can use a lot of those properties. So here we go. Definition. A subset H of a vector space V is a vector subspace, is a subspace if three things hold. Number one, the zero vector is inside of H. H is some kind of a property inside the vector space. There's something special going on about H compared to the general vector space V, where this guy's contained inside. So if the zero vector has that property, whatever H does, then that has to be the first thing. Two, H is closed under vector addition. So if I got two of these vectors that have these special properties from H, and I add them together, the resultant also has this special property from H, which means it's inside of H. So it has, quote unquote, closure under addition. Vector U plus vector V in H, so U and V are in H, vector U plus vector V will also be in H. And you also have to have the closed under scalar multiplication. So if I got this vector U inside of H, and I got this constant C from with a set of scalars here, so it's constant, the product, the scalar times the vector will also be inside of H. C times U would also be inside of H. So subspaces are easier to deal with because I only have to show three properties of these guys. I got to show the zero vectors in there, closed under a vector addition, and closed under scalar multiplication. Scalar times vector is back inside there. So it makes it a lot easier to show. And this is another thing. If I'm out there in the world and I need to create myself a vector space somehow, got to look for the old vector space. Instead of just trying to grab at straws in terms of the space of mathematics, and I'm looking out there trying to go, is continuous functions going to be a vector space? Go through all those 10 properties. Instead of that, if you go and look at something that you know is a vector space, look at all the examples that I've given you. Go grab one of those things, and then look inside of it and see if you see a pattern of some subset of this vector space that has something special about it. And then check these three properties. And all of a sudden, you'll discover there's a lot more vector spaces out there than you realize because you've got this vector subspace, which is a vector space in its own right. So that's what I want to put as a note. Because H is inside of V, a vector space, H is inside of V, which is a vector space, and if all three properties hold, then H is also a vector space. We call it a vector subspace, and the sub means it's contained inside, but it's going to be a vector space in its own right. So instead of just trying to grab at straws looking out there in the universe, go grab yourself a vector space. Look inside of it for some properties that are special, like even vectors or something like that, if you can define these guys. Even plus even is still even. So you've got some nice properties here. You can create some interesting vector spaces inside of vector spaces. You also have some trivial vector spaces. Look at my next example over here, and that is this guy. H is equal to just the zero vector. I'm being very arbitrary here, the zero vector itself. This is a vector space inside of V. V is an arbitrary vector space. You know it has the zero vector. If you look at the zero vector as itself, that's the only thing you got is the zero vector. It's going to be a vector subspace. Let me show you. What is 0 plus 0? There's only zero vectors in there. What's a zero vector plus a zero vector? Zero vector. All right, so it's closed. You get back to zero again. What's any kind of the zero vectors in itself? So the zero vectors there is closed under 0 plus 0 is 0. What's any arbitrary scalar times the zero vector? Take that scalar, multiply it by the zero components. What are you going to get? 0, so you're right back inside there. So the three properties of being a vector subspace are held with just the 0 vector. So 0 is a subspace of any vector space. If you look at the vector space, just look at the element, the vector 0, just him by himself, he will actually create his own vector space. All properties are held. It's considered quote unquote trivial, okay? So, turn my page over here. So, let's start looking at some examples and some proofs. All right, here's an example right here. Let P be the set of all polynomials with real coefficients, with the operations defined on a function. You know, basically, we have polynomials, okay? And we're focusing on addition. That's a big old plus there. So this is the addition of polynomials. And scalar multiplication, scalar in the reals, polynomials. P is a subset of all real value functions. Why is P a subspace of the real value functions? Well, first off, it's a real value function because, well, it's a polynomial. You can plug in numbers into a polynomial and crank out numbers out of a polynomial. It's a real valued function by our definition of real valued function. But this is a subset of real value functions, okay? So, here we go. Why is it a, quote, vector space? All right, so here we go. Number one, if we let P of T equal to 0, okay? Right? This guy right here, P of T is actually equal to 0. This means it's like a 0t squared plus 0t plus 0. This itself is that, quote, 0 vector inside of P. Does that make sense? You can rewrite a 0 polynomial as 0t squared plus 0t plus 0, and that's your vector. So you got the 0 vector inside of a polynomial. You can write 0 as a polynomial is what we're saying. So therefore, the 0 is inside of your polynomial set, okay? If P of T and Q of T are elements of P. These guys are polynomials. And what is P of T plus Q of T? What will that be an element of? What's a polynomial plus a polynomial? It's a polynomial. Why? How do you add polynomials? So an example here in terms of a basic one, here is this. If we let P of T equal 3t squared plus 2t plus 1, and we let Q of T be equal to negative 2t squared plus t minus 5, okay? These are two polynomials. What would P of T plus Q of T be equal to? How do you add polynomials? What is 3t squared plus 2t plus 1 plus negative 2t squared plus t minus 5? What would it be equal to? How do you add polynomials? You just combine their coefficients, right? What is 3t squared minus 2t squared? T squared. What is 2t plus t? 3t. And what is 1 minus 5? Negative 4. So I got t squared plus 3t minus 4. My point to this is that is a polynomial. Arbitrarily speaking, this is how you add polynomials. So therefore, it's still a polynomial. You combine like terms. So you got closure here. And then the third case is this, okay? Let C be a real number and P of T a polynomial in P. Then, what is C times P of T? where would that be located at? Well, how do you multiply polynomials? Again, an example here, let's let C be equal to arbitrarily 3. P of t is equal to 3t squared plus 2t plus 1. What is 3 times P of t? That is 3 times 3t squared plus 2t plus 1. And what do you end up getting on that? 9t squared plus 6t plus 3, which is still a polynomial, because all you're going to do is distribute constant. And you've got constants in front of each term of your polynomial, times another constant, you still got constant in front of your polynomial. This guy is an element of polynomials. So, by definition, P is a subspace of the real valued functions, vector space. So again, we're not talking about rocket science here. We're talking about combining like terms and doing our old basic arithmetic that we've been doing since about the 3rd or 4th grade with this stuff. Okay? So, keep going with this. Where are we going with this? Well, things I want you guys to focus on. Again, where do people have confusion with this stuff? All right, so I got some more examples for you guys, so I wrote them down before class so I can talk about them while you guys are frantically copying the papers. All right, so here it is. R2 is not a subspace of R3. Okay? R2 is not a subspace of R3. Why? Because R2 is not contained inside of R3. Note, R2 is not contained inside of R3. Now, I know what you're thinking, that, well, isn't it? I got 2 components versus 3 components. 2 components are less than 3 components, so therefore it should work. No. Reason why. Now, don't get me wrong. R2 is a vector space. R3 is a vector space, but R2 is not a subspace of R3. And the reason for that is, what does R3 look like? What does R3 look like? Give me an example of R3. Give me a vector in R3. What does it look like? To be inside of R3, what do you look like? A, B, C. That's an element of R3. How many components do you have to have? 3. What does an element R2 look like? AB. This is the element of R2. There is no 3rd component. So this is not contained inside of this, because they don't look alike. You got the vector space must have a certain look to it, and any kind of vector subspace has the same look with a special property attached to it, but it's still got to look exactly like it's contained inside the set. This is 2-dimension. This is 2 components. This has got 3 components. So R2 is not contained inside of R3. However, I could create something or other that is. Question. All right. I could create something or other that looks like R2, but it's not R2, but I can make it like isomorphic to R2. Remember those wonderful words from chapter 1. I can make it isomorphic to R2. So take a look at this example here. So let me draw a little line here so I want to kind of separate the 2. Look at this guy here. Look at H. H is equal to the set A, B, and for the 3rd component, I'm going to put 0. Okay? Where A and B are real numbers. Now, this guy right here is a subspace of R3. Well, isn't it R2? No, it's not R2. You're right. It's got 2 components and a 0 component. put that zero component in the third spot, that makes it a three-dimensional vector, so it's an element of R3. But we're just gonna make that third component zero, and the first two components can be A and B. They're gonna be arbitrary. They can be anything you want them to be. Okay? So, why is H a subspace of R3? Now, I couldn't have just arbitrarily picked that third component. I had to pick him special. So I'm trying to show you that I can write an isomorphism from R2 to the H element in R3 here. By just A goes to A, B goes to B, and that nothing will go to zero, but I gotta have that zero down there. And I couldn't have made him any other number, because for this set H to be a subspace of R3, what are the three things you gotta show me? The zero vector's in there, it is closed under a vector addition, and it's closed under scalar multiplication. So, here we go. Why? You will notice if I let A equal 0 and B equal 0, which are real numbers, then 0, 0, 0 is an element of H. So all I gotta do is pick A and B, can be any real numbers. I pick A to be 0 and B to be 0. That's gonna force the 0, 0, 0 vector to be inside of H. Now I got the 0 vector from R3, which is 0, 0, 0, inside of my H vector. Okay? If I put a 1 down here, then I got problems. I couldn't get the 0 vector in it, and it wouldn't be a set vector subspace. The second thing is, I gotta show scalar addition. So let's let vector u be equal to a, b, 0, and let's let vector v be equal to c, d, 0, for a, b, c, and d being some kind of real numbers. Then, what is u vector plus v vector? That would be a, b, 0 plus c, d, 0. How do you add vectors? What do? You add their components. So, this would give you a plus c, b plus d, and then 0 plus 0, right? Which is of the form a plus c, b plus d, 0, which means he's an element of H. Term, gotta have 0 in the third component. That's the property to be inside of H. And then if I look at c being some kind of arbitrary real number and vector u being equal to a, b, 0, which is inside of H, then what would c times u be equal to? This would be c times a, b, 0, which will be equal to c times a, c times b, and c times 0. That's how you do scalar multiplication, which puts it into the form of c times a, c times b, but c times 0 is 0, which puts it back inside of H. So by definition of subspace, H is a subspace. Where does he come from? To be sub, you got to tell me who the overriding vector space is, and that would be R3. Does that make sense? More examples, just to give you a feel for this wonderful world of vector spaces and subspaces and things like that. Here's my next example. A line that does not go through the origin in R2, so we're talking about, give visual perspective here. A line that does not go through the origin in R2 will not form a vector subspace of R2. Why? Because you've got to have the 0 vector in there. So a line that's the 0 vector is pretty much y equals 0. Y equals 0, x plus 0. Okay, y equals mx plus b. Let the slope be 0 and let the y-intercept be 0. You pretty get 0 horizontal line, but that has to go through the origin. If it doesn't go through the origin, you can get y equals something plus something that's not 0. which does not allow you to have the zero vector in there. So the reason for this is zero vector of R2 is not on or in the line that does not go through the origin. So that's always the first thing when I'm sitting there looking at, is this guy a vector space? Yes or no? I got a 50-50 shot. First thing I'm going to check is the zero vector. Check zero. Whatever the structure they give you, does that have the zero vector in there? Well, lines that don't go through the origin will not put the 0 point or 0 line inside that set. So it's not going to be a vector space. So if you extend this over for all those folks in my class that have had calculus 3, well, if 2 dimensions, you got a line going through the origin. 3 dimensions, we're talking about like planes and space type thing here. The plane R3 that does not go through the R3 origin, which is the 0, 0, 0 point, is once again not going to be a subspace of R for the exact same reason. If you don't go through the origin, then the zero vector will be overlooked, and therefore automatically you do not have a vector space or vector subspace. You've got to have the zero vector in there. Okay? So, turn the page over here. So let's talk about some definitional stuff here. Question for you. All right, give yourself a couple of vectors. I'm just going to call them arbitrarily V1 and V2. From a vector space, V. V is a big old vector space, R27, whatever. Okay, just pick a couple of them. V1 looks like R27 element. V2 is another R27 element or whatever. And I want to define H to be equal to the span of V1 comma V2. Is H a subspace of V? The answer is either yes or no. Okay? Now let's go back, because this is going to be on your next test, which is when? Tuesday. Okay, a week from today. All right, there you go. Question for you. What's the definition of span? Tell me what it means. Very good. It means a set of linear combinations, which means, what does a set of linear combination mean? Well, it means I can multiply any scalar times the first vector and add that to any scalar times the second vector. That is going to get into my linear combinations. That's the mean to be inside the span of a set of vectors, okay? So, the answer is either yes or no. The actual answer is yes, it is, and this is why. Number one, zero vector. All right? The zero vector, okay, we'll just call this guy the zero vector. That's actually equal to 0 times V1 plus 0 times V2, right? This is an element of the span of V1 and V2, which is actually equal to this set H. What it means to be in the span? You can pick any scalar you want, multiply it times one vector, and any scalar times the other vector, that's your linear combination. You just got to pick the right guy. I picked 0. 0 is a scalar, in whatever world I'm willing in, there's a 0 element in there. And 0 times your first vector plus 0 times your second vector is going to actually give you the 0 vector because it kills all the components, but the setup is the same. So 1, the 0 vector is inside of, so the 0 vector is an element of H. Number 2, okay? All right, let U, vector U, and vector W be an element of H. What does that mean, to be inside of H? Well, H is the span of V1, V2. That means that there exists a C and D and an E and an F that are scalars, okay? Such that U vector is equal to E times V1 plus, let's see here, there should be a C there, sorry about that. C, D, E, F, get my letters right. C times V1 plus D times V2. And let's let vector W be equal to E times V1 plus F times V2. That's what it means to be in the span, right? There's some constants out there that I can shovel in front of my vectors and add them together, and that'll give me the vector that I started with. So U is equal to CV1 plus DV2, and W is equal to EV1 plus FV2. Then, what is U plus V? W, sorry, U plus the W vector. This would be CV1 plus DV2 plus EV1 plus FV2. And all you got to do is just rearrange them and factor out your coefficients from the distributive law. So you end up getting C plus E times V1 plus D plus F times V2. And you'll notice that that is an element in the span of V1, V2, which is that the set H. So two holes. Linear combination, again, I'm trying to drum in these definitions. This is stuff you have to have memorized. What does it mean to be in the span? You can write linear combinations. Now, I can pick any constants I want, 3, -4, 45, square root of 2, whatever. I'm just going to call them C, D, E, and F. And then the third one is pick a constant here. I'm going to let it be, I don't know, C, be a scalar, from wherever the world of scalars we come from, and let U, W be equal to EV1 plus FV2 as before. So I got an arbitrary scalar, and I got an arbitrary vector W, which is in the span of the set of these two vectors, V1 and V2. Now, then, what is C times vector W? This would be C times EV1 plus FV2. Well, again, what do we have here? We have the distributive law, which means that I'm going to have CE times V1, and I can use my associativity property because I am in a vector space, but I'm going to show you I'm going to have the same look here. Plus CF times V2, and as CE and CF are scalars, then C times W is an element of the span of V1 and V2, which is equal to H. Three things have held. The zero vector is in there, inside of H. If I got two arbitrary vectors inside of H, inside that span of V1 and V2, when I add them, I'm still inside the span of V1 and V2. And if I multiply a scalar times the element in the span of V1 and V2, I can distribute that scalar, and I'm still inside the span of V1 and V2, which is I'm still inside of H. So these are not overly difficult. So at the end of the day, the answer is a resounding yes, which means we have a theorem. And it's a theorem I've put up before, but now I'm actually emphasizing it. Before I said the span of a set of vectors forms a vector space. Now I'm telling you that if V1, V2, I write to VP is an element of V, a vector space. then the span of any set of vectors, a finite set of vectors, V1, V2, to VP, is a vector subspace of V. That word span means you have that vector subspace, okay? We're going to use that a lot, because I'm going to come back and slap you upside the head with some things you've already done from chapter 2. Great time to review, but you'll see that when I get to section 4.2. So, how can I make it more interesting for this stuff? All right, take a look at this set here, another example. So I'm trying to throw lots of examples with you guys, so you can handle it. All right. Let H be equal to the vector 2s plus t, comma, s minus 4t, comma, 3s plus 2t, comma, t, and then close bracket. This is my, if you had me for calculus 3, this is my classic notation for a classic vector written in horizontally there, okay? This is a vector such that is what that line means. S and T are real numbers. Show that H is a subspace of R4. All right, well, first thing is this. What you have learned, what I have taught you since the beginning, is when we're dealing with vectors, and we were dealing with matrices, all the way from chapter 1, the favorite vector you guys played with were if you looked at a matrix, were what we call the column vectors. They were easy to write up and stuff like that. They were easy to see. We talked about row vectors later, and I've written this thing as a row vector. But how can I write a row vector as a column vector? Is there much difficulty there? No. All we got to do is put the word transpose on it in terms of rows and the columns, right? So I'm going to write this as a column vector. So write the set H, okay, the arbitrary in H as a column vector. You would appreciate that because it's hard to see stuff when it's written in rows because you've been programmed for the columns. So if I did that, I would end up getting this. First component is 2s plus t. The second component is s minus 4t. The third component is 3s plus 2t. And the fourth component is just plain old t. So it's the same vector, it's just been transposed. Okay? Then playing vector algebra on this thing. I've got two variables here. I've got s and I've got t. You see them? Break them apart. So this vector, 2s plus t, s minus 4t, 3s plus 2t, and just t is going to be 2s, s, 3s, and 0, plus the vector t, negative 4t, 2t, and t. Because how do you add vectors? You add components, so I'm right back where I started from. Well, s and t are constants, aka scalars, so you can factor them out now that you've isolated them. So this would also be equal to s times 2, 1, 3, 0, plus t times, factoring out the t, you're left with 1, negative 4, 2, 1. Does that make sense? So, as s and t are scalars, and if we u equal to vector 2, 1, 3, 0, and v be equal to the vector 1, negative 4, 2, 1. This set H is equal to, what do you call this? Linear combinations of these two vectors. H would be equal to the span of vector U and vector V. Right? Because all it is a scalar constant times these vectors. I label these vectors, that's U and that's V. So it's a scale, it's the linear combinations of U and V, which is called the span. Therefore, by theorem, previous theorem, what do we say the span of a set of vectors is going to be? It's a vector what? Subspace. Therefore, by theorem, H is a vector subspace of who? Who's he a vector subspace of? Look at the components. 1, 2, 3, 4, right? Of R4, because we wrote these vectors at 2, 1, 3, 0. That's a vector in R4 because it's got 4 components. Does that make sense? I wrote it as a set of linear combinations. And if you want to, you can sit there and redo what we just did. If you write it like this, a set of linear combinations, the 0 vectors inside there, because you can let S be equal to 0 and T be 0. If you add, a vector looking like this and a vector looking like this, and replace S with A and T with B and add them together, you're going to still have that same look. And I can multiply any scalar times these guys, and it's going to look like these two guys again. So I can go through the definition of subspace if you want me to, but it's nice to know if you can write a set of vectors as a span, a set of linear combinations, you can stick a flag in it, salute it, and declare victory. You've got yourself a vector subspace. Okay? But that's kind of the game plan here. So I got another problem for you before we move on to section 4.2. And that is another example. See if we guys can do it. Okay? Question is this. K is equal to the vector 2a plus b, comma, b minus, that's a minus right there, b minus 1, where such that a and b are in R. Is K a subspace of R2? We do have two components here. So is this K going to be a subspace of R2? Well, that's the question. The answer is either yes or no. Okay? So may I make a recommendation? Do what we did the last time. Because you guys are not comfortable, typically, right now, with row vectors. Let's write them as a column vector. So you can write this vector 2a plus b, comma, b minus 1 as a column vector as 2a plus b and then b minus 1. Now, it makes it a little bit easier to see, so my standard question is this thing going to be a subspace, yes or no? What's your feeling? Well, we'll make it a democracy. We're going to have to vote real soon here. All right, so who votes for the amendment here that this is a vector subspace? That no, it is not a vector subspace. 6 people. That happened way back when in the election. I don't think it was the last election we had, but everybody seemed to vote. People that didn't even supposed to vote voted on that one. But elections before that, people didn't vote, and you know what happens when people don't vote? You get the poorest of candidates. So we need to vote. So vote. Your vote counts, maybe. Because there is a real answer here. Get the right candidate here. Is this thing a vector subspace? Yes or no? What's your feelings? I hear yes, and I hear no. Okay, so, great. All right, why yes? All right, you've got two components, right? So with the two components, we're clearly inside of R2. I'll give you that. You're definitely inside of R2. But A and B are arbitrary constants. Based upon any constant I can put in there, are we going to have those three properties of being a vector subspace? Zero vector's got to be there. It's got to be closed under addition and scalar multiplication. For the nodes, why do you think it's not going to be in there? Why not? Well, we can't pull A out of row 2. Well, it doesn't need an A. Doesn't have an A at all. So it's 0 for that part, so you can do that way. All right, that's one way of looking at it. If you expand this thing with the A, B type thing here, you're going to get this. So this would be what? 2A. There's going to be 0 right there, right? This is the A part. Plus, what's the B part? This will be a B here, right? And there's going to be a B here. Your problem is this minus 1. Plus, you've got the 0 minus 1. And this guy is not being scaled. That right there makes it different from the last example that we did. So that's an excellent notification. But that doesn't prove or disprove anything. You just wrote them differently. So, if you got a feeling that it's not because of this special something without a scalar on there, you got to tell me why. Let me show you. All right. First things first. Go back to your definition. Is the 0 vector, an element of K? Can you come up with some constants, A and B, that make the 0 vector in there? The answer for that is yes. If you let A be equal to -1/2, it's just a scalar, a real number, right? And you let B be equal to 1. Now, I had to set B equal to 1 because I want the 0 vector. I got B minus 1, right? I want to make that 0, so B's forced. It's got to be 1 to put the 0 vector in there. But if I do this, then the 2A plus B, B minus 1, ends up with these constants here. You end up getting 2 times -1/2 plus 1 over 1 minus 1. Well, last time I checked, that is 0, 0, which is an element of K, so the 0 vector is inside there. First thing is, check the 0 vector. Usually if it's going to screw up, usually, not always, but usually if it's going to screw up, it'll be with that darn 0 vector. You won't be able to get 0 in the darn thing, okay? But we can with the correct choices for A and B. A's got to be -1/2, B equals 1, that works. Puts the 0 vector inside of K. Question? Okay, try this. If A and B are 0, do you get the 0 vector? 2 times 0 plus 0 is what? What is 0 minus 1? -1. That's not the 0 vector. That's the vector 0 minus 1. So, not always. That did not put it in there. But I did pick some of the correct constants that did allow the 0 vector to be in there. It was just so happened it wasn't 0, 0. Usually it is 0, 0. Usually. But not in this example because I'm trying to go for the strange examples. But now, let's talk about the next thing. Vector addition. So, watch this. All right. So, for A, B, and I'm going to do 2 more, C and D, elements of the reals, we have the vector 2A plus B, B minus 1, and do 2 more constants. 2C plus D, and D minus 1, elements of K. They have the form K. All I did was replace A with C and B with D, so it's the same format, so they're in the same form. Add them. Let's see what you get. what is 2a plus b, b minus 1, plus 2c plus d, d minus 1. Tell me what you get. Well, when you add vectors, you just add their components. So I get this. 2a plus b plus 2c plus d. I get b minus 1 plus d minus 1. Let us clean that sucker up. Combining like terms, this would be 2a plus 2c, I'm putting my 2's together, plus b plus d, and then I get the b plus d minus 1 minus 1. I'm putting my constants together into minus 1 minus 1. So watch this. Look at the first component. I could factor out a 2. Remember, I'm trying to make it of this format. I got to look like this. And here's my problem. This will give me 2 times a plus c plus b plus d. But then down here, I'm going to get the b plus d. But what's a minus 1 minus a 1? It's 2. Is that the format of what k is supposed to look like? It's got to be 2 times somebody plus somebody, but that somebody there has to be this somebody minus 1. There's my somebody, and there's the same somebody, but no longer is it minus 1. What is it now? Minus 2. And that's not the format, so that's not an element of k. So the answer is no, k is not a subspace of R2, and R2 because you had 2 components there. Does that make sense? So, in the essence that when I plug in that 0 we were just talking about, when I plug in the constants as zeros and I don't get the 0 vector out of it, that's usually a clue that probably not going to be a subspace. But usually you have to argue a little bit further down of why it's not, and it's the closure that messes you up. It's that constant. And when you add a couple of constants together, you're going to end up getting a bigger constant. In this case, a negative 2, which messes you up when it's supposed to have a lookup of minus 1. Yeah?
So just to be clear, mine is not a subspace because it's minus 2.
Right. If it was a minus 1 there, then it would have followed the same pattern, and then it would have been a subspace. And then I would go on to seeing how scalar multiplication would have worked. It's the scalar, it's the vector addition, closed under vector addition that caused me my problems. A minus 1 is a minus 1, minus 1 minus 1 puts a minus 2 on it, and you're supposed to have that minus 1 look to everybody. So, does that make sense? All right. Well, since we're talking about vector subspaces and the like in different kinds of spaces, let's go back to something that is on your test, so it's a great time to review. Null spaces, column spaces, row spaces, and linear transformation. We throw the word spaces on there. You know why? Because each one of these guys is going to be a space or a vector subspace of some R somebody, Rn, Rm, or something like that. Okay? So let's go back and review definition. What is the null space of a matrix A? So you got a matrix A. So the null space of a matrix A called null A is equal to, and this is a set notation, it's a set of vectors X such that X comes from Rn. That little line means such that. This is how you would read that notation. So the null space of A is the set of vectors X such that X comes from Rn and A times X is equal to 0. Is the null space of an M by N matrix A, so, and it is the set of all solutions of the matrix equation, AX equals 0. So if A is M by N, you multiply it by vector X, it's got to be, and it's a vector, so it'll be N by 1. That's why N by 1 is a vector of Rn, okay? So, the null space is the set of solution vectors of AX equals 0. Equation proof. Look at this example. I've got 2x1 plus x2 minus 3x3 is equal to 0. I got x1 minus 2x2 plus 5x3 equals 0. Now, first off, trying to go easy on you guys because it's been a while since you looked at section 2.8. Vector u is going to be the vector 1, 13, 5. Is vector u in the null space of A? Yes or no, basically, is my question here. Why? You guys can't just go yes or no. We don't do that without explanation. Okay? So the first thing I would do, since we're talking about null spaces, is you should write as a matrix equation. I gave you a system of equations, so this goes all the way back to chapter 1 and the basic stuff here. Rewrite this guy as a matrix equation. What would it look like? What would my matrix look like? It'll be 2, 1, negative 3, 1, negative 2, 5, multiplied times x1, x2, x3, and it would be equal to 0, 0. Double check me. What size is my quote-unquote matrix A? What size matrix does this do? It is 2 rows by 3 columns. It is a 2 by 3. What size vector am I looking at for x1, x2, x3? This is a 3 by 1, and it's equal to the 0 vector, but because it's matrix multiplication, the 3's match up and cancel. You're left with a 2 by 1. That's exactly what we got. It's a 2 by 1. Okay? Classic matrix multiplication from chapter 1. So, here we go. The question again is this. Is vector u in the null space of A? Well, there's only one way to find out. All right, so here's my matrix. 2, 1, negative 3, 1, negative 2, 5. Let's put in the u vector, A. Let's multiply it times u. What was my u vector? It was 1, 13, 5. And let's see what we get. If you get 0, the answer is yes. If you do not get the 0 vector, then the answer is no. So here we go. 2 times 1 plus 1 times 13 plus 3 times negative 3 times 5. Second row, 1 times 1 plus negative 2 times 13 plus 5 times 5. See what we get here. This will be 2 plus 13 is 15. Negative 3 times 5 is negative 15. 15 minus 15 is, yep, that's 0. This is 1 times 1, which is 1. Negative 2 times 13 is what? Negative 26. 1 minus 26 is negative 25, plus 5 times 5, which is 25. Negative 25 plus 25 is, it's 0. So I got 0, 0. So answer the question. Yes or no? Well, the answer, of course, is yes. U is an element of the null space of A. Because when I plugged it in with my matrix multiplication, I did get the 0 vector. And that's, to get the 0 vector means you're in the null space. If you don't get the 0 vector, you're not in the null space, okay? So, the null space of an m by n matrix is a subspace of Rn. So it ties back to what we were talking about in terms of subspaces. The null space is a subspace of Rn. Remember, A is m by n, so the vectors that set it equal to 0 are going to be n by 1, which means your null space is a subspace of Rn. Okay? So let's do one from chapter 2.8, which would be on your next test. What a null space of this thing. This is something you should do because this really is on your next test. So, gave you a matrix A. 2, negative 4, 5, 8, negative 4, negative 3, 6, negative 1, 1, negative 7, 1, negative 2, 2, 3, negative 1. All right, how do you find the null space? Let's go back to the basics and see if you've learned something throughout the semester here. To be in the null space, you've got to go for that matrix equation. AX equals 0, right? How do I solve for x? Well, first off, let me just throw some major stuff at you guys, reminding you, because I'm getting to review for the test here. Well, AX equals 0, one of the things I could do is find A inverse. Can you find A inverse on this guy? Yes or no? Why not? You're shaking your head.
It's not like a square root.
Thank you. That's all I needed to hear. Only square matrices have inverses. Okay, this sucker's not square. This sucker is 3 by what, 5? It's not square. So don't go with the inverse bit because you can't. Only square matrices have inverses. If it was square, you can consider it. But how do we typically solve AX equals 0? Especially when it's not a square matrix, there's only one way. What are you going to do? We're going to take A and do what? Officially augment with 0 and solve it like we typically do when we have, a matrix AX equals B. We would put B over here, but because it said equals 0, B equals 0. So, and then we're going to do, which would give you this, augment your matrix, and then we'll talk about what to do. 2, -3, 1, -4, 6, -2, 5, -1, 2, 8, 1, 3, -4, -7, -1, augment 0, 0, 0. Now, what are you going to do? Give me strategies first, so you know what to do on the test. What's your strategy? So what are you going after first? Give me your strategy. RREF, row reduced echelon form. Excellent. We're going for RREF, right? So to go for this elusive RREF, what's your first move? Swap, row swap. So that would be R1 with row 1 with row 3, I think is what you're telling me. That would give me 1, -2, 2, 3, -1, officially augment with 0. -3, 6, -1, 1, -7, 0, and then 2, -4, 5, 8, -4, augment with 0. Now, what is my next move? Take that pivot, that's the whole point, sweep down. So that'd be 3 times row 1 added to row 2, and then kill off that guy, and then -2 times row 1 added to row 3. Remember, whatever row you add to is the row you replace. So I get 1, -2, 2, 3, -1, augment with 0. Here we go. 3 times 1 is 3 plus -3 is 0. 3 times -2 is -6 plus 6, well, that's nice, that's 0. 3 times 3 times 2 is 6 plus -1 is 5. Okay? 3 times 3 is 9 plus 1 is 10. 3 times -1 is -3 plus -7 is -10. And I love the zeros. 3 times 0 plus 0, it's still 0. So far, so good. Double check me on this so you don't screw up your basic arithmetic. Now sweep down and kill off that 2 with the -2. -2 times 1 is -2 plus 2 is 0. -2 times -2 is 4 plus -4 is, that's nice, 0. -2 times 2 is -4 plus 5 is 1. All right. -2 times 3 is -6 plus 8 is 2. -2 times -1 is 2 plus -4 is -2. And 2 times 0 is 2. 2 times -2, excuse me, -2 times 0 is 0 plus 0 is still 0. What's your next move? What would you do? Doesn't matter, I can do 1 or 2 things. I could. Or I could just multiply row 2 by, all right. Whichever is easiest. I'm gonna go with 1/5 times row 2, but you're right, I would have accepted swapping the row 2. So this gives me 1, -2, 2, 3, -1, augment with 0. Now this would be times 1/5, that'd be 0, 0, 1, 2, -2, 0, and I got 0, 0, 1, 2, -2, 0. what do you happen to notice on this one? It's getting better all the time. No fractions, you should really appreciate that. But what do you happen to notice now? You got the two rows are the exact same thing, right? So that's gonna kill off one of the rows. So basically, sweep down, negative row two plus row three, replace row three with that. You get one, negative two, two, three, negative one, augment with zero, 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 one, two, negative two, zero, and zero, 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 zero. I got one more move. What's my move? Sweep up. Negative two times row two, add it to row one. So this makes row two the same, zero, zero, one, two, negative two, augment zero, 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 and sweeping up. Zero times negative two is zero, plus one is one. Zero times negative two is zero, plus negative two is negative two. Negative two times one is negative two, plus two is zero, that was the point. Negative two times two is negative four, plus three is negative one. Negative two times negative two is positive four, plus negative one is three. And negative two times zero plus zero is still zero. So I got it down to that. But I wanted you to find a null space. All that work, we're almost there. Now, what are you gonna do? Find the null space. You wanna find the solutions where AX equals zero. What we typically do from there, again, reminding you from chapter 1, is I write it back as equations. So this would be x1, x2, x3, x4, x5. So x1 minus 2x2 minus x4 plus 3x5 equals 0. And the second equation is actually x3 plus 2x4 minus 2x5 equals 0. What's my next move? Again, reminding you from chapter 1. What's that? No, not add them together, no. Solve for the pivots, the pivot terms, all right? You're right. So these were my pivots. How many pivots did I have? 2. Solve for the pivots. I'll put that in there for your notes. Solve for pivots. This will give me x1 is equal to, move everything to the other side, 2x3 plus, 2x2, sorry about that one, it's 2x2, plus x4 minus 3x5, and x2 would, x3, put my coefficients there, x3 would be equal to a negative 2x4, I'm trying to line these guys up, plus a 2x5. Moving them to the other side, change their signs. Now, you're supposed to write it as the famous, write it as a vectored, a parametric vectored form. Thank you. Parametric vectored form. So, x1, x2, x3, x4, x5 equals, okay? x2 is equal to, here we go, it is equal to 2x2, so this would be 2 times x2 plus x4 minus 3x5. x3 is going to be equal to a negative 2x4 plus 2x5. There's only 2 pivots. What does that make the other variables? Free variables. And free variables are equal to themselves. So x2 equals x2. Notice I'm trying to line these guys up. x3 was equal to that. That's not these were the 2 pivots, x1 and x3. So x4 is equal to x4, and x5 is equal to x5. And one more move. I get x1, x2, x3, x4, x5 is equal to, factor out the x2, you're left with the vector 2, 1, 0, 0, 0, plus, factor out the x4, you're left with a 1, a 0, a negative 2, a 1, and a 0. and then you're left with, factor out the x5, you're left with a -3, 0, a 2, a 0, and a 1. Does that make sense? My question still stands. What is the null space of A equal to? This is a set of linear combinations, right? So it is the span, because that's what the word linear combination means in terms of my terminology, of what vectors? You've got 3 vectors, 2, 1, 0, 0, 0. You've got the vector 1, 0, -2, 1, 0, and you've got the vector -3, 0, 2, 0, 1. And we have a theorem that says, quote unquote, the span of a set of vectors makes a vector subspace. That was my theorem. So the null space of A, which is these 3 vectors, the span of these 3 vectors is a vector subspace. But notice how we solved for it. Something very important. It's going to be on your test a week from today. So study hard on this one. We'll review on Tuesday, and I will help with your review. I'll keep going on chapter 4. If you guys don't have questions other than homework, I'll go over any kind of homework questions or whatever, and I'll do a few more of these problems which kind of link back to our chapter 2 and chapter 3 material. So study hard on this stuff, and I'll see you guys on Thursday with, don't forget, homework due, so bring it at the beginning of class, turn it in.